In this video, we're going to look at how to find the general term for any quadratic sequence. Now remember, a quadratic sequence is one that has an n squared in the general term, and the way we can identify a quadratic sequence from a list of numbers is by looking at the second difference and noting that the second difference must always be the same. So to start with, we're going to look at an example when we know the general term, and then we'll look at some examples where we don't know the general term. So here we have un equals 2n squared minus n plus 3. So the first thing we need to do is generate the sequence. When n is 1, we get 2 times 1 squared minus 1 plus 3 gives us 4. When n is 2, we get 2 times 2 squared minus 2 plus 3 is 9. When n is 3, we get 2 times 3 squared minus 3 plus 3 is 18. When n is 4, we get 2 times 4 squared minus 4 plus 3, which gives us 31. And when n is 5, we get 2 times 5 squared minus 5 plus 3, which is 48. Now we're going to work out the first difference. We often use the notation triangle 1. Well, triangle is actually the Greek letter delta, and we often use that letter in maths to mean the difference. So the first difference is triangle 1 here is 5, and then 9, and then between 18 and 31 is 13, and then it is 17 there. And then we are going to look at the second difference. The second difference here is 4, 4, and 4. So the second difference is always the same, which means we are dealing with a quadratic sequence, which we know because at this point we actually know what the general term of the sequence was. So to work this out, to work backwards from here to find the general sequence, we actually need to consider the general quadratic sequence. The general quadratic sequence is of the form an squared plus bn plus c. And we do exactly the same thing as we did with the last one. When n is 1, we get a times 1 squared plus b times 1 plus c, which just gives us a plus b plus c. When n is 2, we get a times 2 squared, so that's 4a, plus b times 2, well that's 2b, plus a c. When it's 3, n is 3, we get a times 3 squared, well that's 9a, plus b times 3, well that's 3b, plus a c. When n is 4, we get a times 4 squared, so that's 16a, plus b times 4, so 4b, plus c. Now we can look at the differences. The first difference, well, the difference between the first two terms, there's 3a's difference and there's 1b difference, because we've got 4a minus a to give us 3a and 2b minus b to give us b. The difference between the second and the third terms, 9a minus 4a gives us 5a, 3b minus 2b gives us b. Difference between the third and fourth, we've got 7a, and then 4b and 3b gives us plus b. Now we look at the second differences. 3a to 5a is 2a, b to b, there's no b's. 5a to 7a is 2a, b to b, there's no b's. And this is our general table for a general quadratic. And when we have this, we can compare it to the table we have for the example sequence, and when we compare it, we can find the values of A, B, and C. So, going back to our example here, the first thing we're going to use is this number at the bottom. And that 4, going back to the general, is equal to this here, to the 2A, because they're both in that bottom left-hand corner. So what we know from that is that 2A is equal to 4, and what that means is A is equal to 2. Now we move up a run and we look at the one on the left hand side of the first differences. We have 5 in our example, and in the general one we have 3A plus B. So what we know from that is that 3A plus B is equal to 5. But we know that A is equal to 2 because we worked it out in the last part. So we've got 3 times 2, so that's 6 plus B equals 5, which gives us B is equal to minus 1. And now finally we look at the one up here, the first term, which is 4, and looking at the general sequence we have A plus B plus C. So once again we compare those two. This time we get A plus B plus C is equal to 4, but we know A is 2 and we know B is minus 1. So we have 2 minus 1 plus C is equal to 4, which gives us C is equal to 2 minus 1 is 1, so C must be equal to 3. Now that we've got that, we can write out our general term by using A, B and C in the AN squared plus BN plus C. So UN is equal to AN squared plus BN plus C, but in this case A is equal to 2, so we have 2n squared. B is equal to minus 1, so we have minus n. And C is equal to 3, so we add on 3. And if we compare that to what we started with, we see that it is the same as the general quadratic sequence we started with at the beginning of the example. So this table here is really important, in particular the 3 values circled there. So let's have a look how we can use it on a couple of examples that we don't know the terms, the general term for. So the table is at the top, that's what we're going to be using, and the example is along the bottom, 2, 0, 0, 2, 6. The first thing we do is we find the first differences. So the first differences are minus 2, 0, 2, and 4. The second differences are 2, 2, and 2. As the second difference is always the same, we are dealing with a quadratic sequence, and now we can compare parts of the general rule table at the top and the example table at the bottom. So we compare the 2a with the 2. So, moving that bit there, didn't mean to do that. So if we move up a little bit, we can have 2a is equal to 2, which gives us a is equal to 1. So that's our first part, a is equal to 1. Now we can compare 3a plus b with minus 2. 3a plus b is equal to minus 2, but we know a is 1, so it's 3 plus b equals minus 2, which means that b is equal to minus 5. Sorry, that there should be minus 2. I was jumping a step. minus 2, so b is equal to minus 5. Finally, we have to do the last step, a plus b plus c, and 2, we compare those. So we get a plus b plus c is equal to 2. But we know a is 1 and b is minus 5. So we get 1 plus minus 5 plus c is equal to 2. And that gives us an answer of c equals 6. Now we put all that together into our general term and we get un equals 1 times n squared, so n squared. B is minus 5, so it's minus 5n. And c is 6, so it's plus 6 on the end. Okay, let's look at one final example. Again, we have the table at the top, and this time we are dealing with the sequence minus 5, 4, 19, 40, 67. Again, the first thing we do is look at the differences. So the first differences are 9, 15, 21 and 27. And the second differences are 6 and 6 and 6. Okay, so we are dealing with a quadratic sequence here because the second differences are all the same. And then we compare the two tables. So the 2a there goes with the 6 there. So 2a is equal to 6. That gives us a is equal to 3. Now we compare the 3a plus b with the 9. That gives us 3a plus b is equal to 9. But we know a is 3, so we get 9 plus b is equal to 9, which gives us b is equal to 0. And finally, we have a plus b plus c, and we compare that with the minus 5. So we get a plus b plus c is equal to minus 5. A is 3, b is 0, plus c is equal to minus 5. And that gives us a value of c is equal to minus 8. And we put all that together and we get un is equal to a is 3, so it's 3n squared. B is 0, so we have 0 n's, so we don't write it. And c is minus 8, so we have minus 8. This method of using the differences is one way to find quadratic sequences and their general terms. In the next video, we will look at an alternative method for doing this, which uses the fact that the second difference is always equal to double the value of a. Both methods can then be extended to look at other types of sequences, such as cubic and higher powers of sequences. Remember, the method works by using the table for the general quadratic sequence and comparing 3 parts of it to 3 parts of the examples table. The 2a with the second difference, the 3a plus b with the first difference, and the a plus b plus c with the first term of the sequence.